Hi, welcome to Math Minute. My name is Adam, and today we're going to be talking about concavity in the second derivative and how they're connected. So first of all, I just have written up here concavity and kind of an explanation on how the test works. So as you know what concavity is, I'll draw a couple pictures real quick. A function is concave up if it looks like this, and concave down if it looks like this. It's kind of intuitive, but just a quick refresher on what they are. So we know that if the second derivative is greater than 0 on an interval a to b, then the original function is concave up on that given interval ab. Now similarly, if the second derivative is less than 0 on an interval ab, then f of x, the original function, is concave down on that same interval. So I'll go through an example of a function, but first I want to talk about an inflection point. Now this is really important. An inflection point is a point where a function f of x changes concavity. This is known as an inflection point. Now this is probably kind of similar to, I want to say, a critical point. You're probably thinking the same thing, but just with the second derivative. Well, as you know with the first derivative, there's actually specific examples where this won't work every time. Now what this says is, if the second derivative equals 0 at a certain point, this doesn't imply an inflection point, but the opposite is true. Confusing. So what this is saying is that an inflection point means that the second derivative equals 0, but the second derivative does not mean that it's an inflection point. So what that says is, I'll draw this example real quick. As you can see, if we start with the function f of x equals x to the fourth, that's the first derivative, and the second derivative looks like that, and then the first derivative looks like that, then the second derivative looks like this. So we know that the second derivative equals 0 at that point, but there's no inflection point there because we're concave down over the whole interval. So that's what this warning says, that it's very important to not jump to that because it's very common, and I remember doing it myself when I took the class. So now I'm going to go back to this and we'll talk about concavity and how this works, how we can test for it. So if we're given the function f of x equals x to the third, we want to find out where this is concave up, where it's concave down from the second derivative. So what this says is, if f double prime of x is greater than 0 on an interval. So let's check where that's true. So in order to get to the second derivative, I've drawn this step, the in-between, the first derivative. We don't have to use it, but it's just to get to the second derivative. So the second derivative, where is it greater than 0 on this function? Well, we know it's from here to here, which is 0 to infinity. So we can say that the second derivative is greater than 0 on the interval 0 to infinity. Okay? Now what that implies is that this says that the original function f of x should be concave up on that same interval. So if we plot that out, 0 to infinity, that's obviously concave up here. So that checks out. Now a similar idea, we want to say, when is the second derivative less than 0? That's what the second requirement is. If f double prime of x is less than 0 on an interval, then the function is concave down. So we're checking here again. So as you can see, this is all below the x-axis. So from negative infinity to 0, the second derivative is less than 0. So we have negative infinity to 0 is less than 0. So let's go check this again with our original function. Negative infinity to 0. That's obviously concave down. So that part checks out as well. Now this last part, we're talking about inflection points. We can't start here and work this way. We can go from here to here because we know that concavity changes from here to here. The inflection point occurs at 0. So what we can say is that we know that this has to equal 0 when we're at 0. Now, looking at this, I couldn't just say, okay, because the second derivative equals 0, I know that has to be an inflection point. I pointed out down here as where that cannot work. When f of x equals x to the fourth, that's an example. So with this test, this can help you find when functions are concave up, when they're concave down. And now keep this in mind, that's the most important thing I want you to take out of this video, is that that does not imply that. So this has been concavity, how the second derivative helps you find that, and we'll hope to see you next time.